Okay, yesterday we talked about the space vector modulation, okay? And we derived the equations for obtaining the time intervals, let's say T1 and T2 in this example, in which I have to apply the space vector V1 and V2 in order to synthesize a rotating vector which is lying within the sector 1. Okay, this vector was VU, okay, and it has a magnitude which is alpha VD, and then he has a position which is theta. Okay, so it is something which is distant an angle theta from the vector v1. Then we should remember that the position of the space vector v1 is, say, 30 degree up the horizontal axis, and then we have 60 degree from v1 and v2. Vu is the rotating vector representing the three-phase systems that I want to get at output of the line-to-line voltages of my three-phase inverters, while V1 and V2 represent 2 out of 8 different possible switch combination representing specific discrete values of the line-to-line voltage. Okay, I showed that basically by considering possible vectorial representation, vectorial, say, synthesis of vector, I can synthesize any kind of vector, rotating vector VU. It is something which provides the best results to use in this synthesis the space vector that bounds the sector in which the rotating vector is placed. Okay, for example, in this case, the vector blue vector rotating is inside the sector number 1, and so that means that I have some advantage if I use the two, say, fixed vector V1 and V2 that bounds the sector number 1 in order to synthesize VU. Okay, the switching words is 100 and 110 for this vector, for these two vectors, and so we derived that the time interval T1 during which I have to apply the space vector V1 over Ts, which is the total switching period, is alpha, a cosine of theta plus p divided by 6, T2, which is the interval in which I have to apply V2 for synthesis of the rotating vector Vu, is alpha sine theta, and then I have also to apply the 0 space vectors, both the 0 V0 and V7 null vectors that are defined as 1f 1 minus T1 over Ts minus T2 over Ts. Okay. In the slide, I defined this quantity as alpha sine p divided by 3 minus theta. They are totally equivalent. Okay. Proved by trigonometric, say, equivalence. You should use something like sine, say cosine, oh nice, the The whiteboard is not working. Sorry about this inconvenience. I hope to solve soon. Okay, good. Okay, because for example, you have that cosine alpha is sine of p f minus alpha. So if you use these equivalents, okay, you can transform the cosine of theta plus p divided by 6 into sine p divided by 3 minus theta. Okay, so nothing that is so complicated to understand. So this happens for the what happened in the sector 1, of course, when the blue vectors, the rotating vectors, stay in its evolution changes the sector which is placed. For example, he who goes here, then I have to perform similar computation for deriving T2 and now a vector which is, let's say, T3 in order to synthesize this vector. Okay, but basically the method and the procedure I show you for the sector number 1 can be employed for all other 6 sectors. What is the basic assumption of this kind of computation? In order to make the synthesis of a rotating vector by using two, say, fixed vectors, like for example v1 and v2, of course, I need that during the switching interval Ts, the rotating vector basically should not move from its position. So it means that the switching frequency should be much higher than the fundamental frequency component of the output three-phase voltage system. Okay, this is the basic assumption. So basically, once we know alpha and theta, which is the position, so the length of this vector and the position with respect to the space vector number 1, we are able to compute this kind of time interval, okay, synthesizing this vector. The question here is how much is this alpha? Okay, so in other terms, which is the maximum amplitude of the fundamental component of the output my three-phase line-to-line voltage system I can get using the space vector modulation. Okay. Remember the discussion that we had yesterday about the use of the zero, the null states, in order to modulate the amplitude of the resulting rotating vector. Okay, just to remember you, I said that basically T1 and T2, so the time interval in which I apply the null, the active, space vector, must be chosen in order to, say, synthesize a precise position theta. Okay. So, for example, we had this example. In which you have T1 and T2. Let's say T1 and T2 in this way, and VBC, which is, for example, this one. Okay, the average value of these two quantities provides, let's say, a synthesis of a vector that are in a specific theta position. What about alpha? Alpha is defined by using the null, the application of the null vectors. Okay, so if we apply the null vectors, you are able to modulate the average value, so the amplitude of this vector, without changing, let's say, the position theta. And as I said in that situation, when you do not apply any t zeta, you have the maximum possible amplitude. When you apply T zeta, what happens that you apply a zero, say, an interval in which the voltage are both zero, and so you are, say, reducing the duty cycle. Duty cycle of a function which, say, is periodic here without T zeta is higher than a function which Ts is here after applying T zeta, because you're applying something which is zero. So the application of the null state reduces the magnitude. So the maximum amplitude you can have for any rotating vector you want to synthesize is obtained when T zeta is zero. Okay. So if we are searching for the maximum possible magnitude of the three-phase line-to-line voltage system for the fundamental component, then we should consider that this happens when the time interval in which we apply the null state is zero. So T zeta must be zero to get the maximum alpha. And so this is, let me put here Ts. This is 1f of 1 minus, I have T1 over Ts, which is this expression, which alpha now is the maximum possible value. And then I have T2 over Ts, and T2 over Ts is given by this expression, so alpha max. Okay, so when T zeta is zero, alpha is the maximum value. So from this expression, we can have that alpha max is 1 over sine So what happens here is that this maximum alpha is not a unique value. It depends on theta. So let me consider the complex plane in which we have the space vector representation. We have, for example, the space vector v1, v2, v3, v4, v5, and v6. And then the two null vectors in the origin of this plane. Okay. So for example, theta is the angle which is measured starting from the space vector v1. Say. So when theta is equal to 0, then you have alpha max for theta equal to 0, which is 1 over sine p divided by 3. And this is 1 over square 3 over 2. So it is 2 over square 3. It is 1.15. Roughly. So, for example, it is here. But changing alpha, of course, this amplitude here is not the same because it depends on theta. So, which is the minimum value that it can be, you can obtain changing theta? So, basically, if you have delta alpha max over the theta equal to 0. You get this over the omega t. If you get, or the theta if you want. If you get this expression here, you can see that the minimum alpha max occurs when theta is p divided by 6. So exactly here, in which for theta, the alpha max, you can say minimum, the minimum of all the alpha max I can have with you by using this expression here, okay, is for theta p divided by 6, and this is 1. Okay, so it's a vector a little bit lower. This is 1.15, then we have here 1. Okay, so remember, so if you say continue this analysis for each theta, you can say that for theta equal to 60 degree, you can get again 1.15, etc., etc., etc. The points in which you have the maximum alpha max lies on the periphery of an hexagon like this one. So these are the points at which you have alpha max as a function of theta. If you want another plot, that is the plot that I put on the slide, is the plot of alpha max as a function of theta from 0 to p divided by 3. So in the sector 1, this is sector 1, and you can have something like this, which the minimum is exactly at p divided by 6. The minimum here is 1, the maximum is 1.15. Okay? And this is the function that I showed you before. So now we have to understand that this vector, so the representing the rotating vector, so the three-phase fundamental component of the line-to-line voltages, has an amplitude which is not constant, depends on theta. But typically, most of the time, I have to say, what I want to generate at the output of any inverter is a three-phase voltage system in which the amplitude is constant. I can modulate this amplitude. I can change according to what is more suitable for my loads at that time instant. Okay, but when I consider an amplitude of my output frequency fundamental component, then this amplitude must be constant. Okay, I don't want a sine wave which is modulated depending on theta. Okay, so which is the only possible constant voltage I can have for all the theta, say, around this plane. But the possible value that I can obtain for each theta is the minimum one. I can obtain the minimum one here, but I can obtain the minimum one also here, and here, and here, etc., etc. So the only possible value that is, say, the maximum value which can be common for all the theta position is the minimum one. Okay, it's easy to understand this by considering the circle which is inside this hexagon. Okay, these represent, let's say, the rotating vector having the same amplitude for each position theta you can have in this complex plane. Okay, so this is the maximum amplitude I can obtain independent from theta. Okay, and so this amplitude is 1. So the minimum alpha max, which is valid for any theta, is 1. So it means that the maximum alpha that I can obtain is 1. So the total amplitude of the fundamental frequency component of the line-to-line phase voltage system at the output of this inverter is Vt. Vt is the maximum amplitude of the fundamental frequency of line-to-line voltage. Vd. Remember what happens in sinusoidal. Compare this result what the results we had for sinusoidal pulse width modulation. With sinusoidal pulse width modulation, we have the fundamental component, the line-to-line voltage, as a maximum voltage, which is Vd squared 3/2 for MA, which is equal to 1. And this is 0.866 Vd. Now we have a result in which the maximum amplitude that you can obtain is 1. So we are able to, say, enlarge by more or less the 15% the maximum amplitude of the fundamental frequency component, still remaining in a situation which is considered to be linear. Okay, so here we have the same results of third harmonic injection. Even in the third harmonic injection method, we are able to are in the linear, let's say, region operation by increasing by 15% the maximum fundamental frequency component of the line-to-line voltage. Okay, so the same results I can have here. Now I want to just discuss a little bit with, say, in a say basically graphical method, let's say, what I mentioned in these lectures about the space vector modulation. So the possibility to say increase the symmetry of the function of the waveform, the switching function that I can have in this technique, in order to decrease the harmonic content I can have in the output spectrum. Okay, for example, I mentioned this fact when I introduce the t zeta time interval. Remember that I said basically I need a null vectors to modulate the amplitude of my fundamental frequency component of the line-to-line voltage. Okay, but what is most of the time is performed, it use both the null states that are, say, the V0 and V7. Okay, there is no mathematical reason to apply both of them. Just one is enough in order to modulate these, because both of them give us 0 for the line-to-line voltages. Okay, but we need to apply both of them in order to, say, enhance the symmetry of the waveforms I can obtain. And with the same reasoning, I said that typically T0, so the time interval in which I apply the null state V0, and T7, which is the time interval in which I apply the null state V7, typically are the same, and I call these are T zeta, okay, for the same reason. Okay, so let me just justify a little bit graphically this behavior, okay, to give you more insight into this characteristic. So we are talking about the sequence of application of the space vectors. Okay, so sequence of the space vectors. So first of all, just to point out the basic, the main characteristic of this method. Suppose that this rotating vector I'd like to synthesize, okay, so the line-to-line frequency component, fundamental frequency component, VU, lies within the sector number 1. So the sector which is bounded by the two active vector V1 and V2. For all the time interval in which this vector VU is within the sector number 1, I have to apply V1 and V2 alternatively in a periodic fashion. The application in time interval for V1 and V2 changes depending on theta. But I have to, say, modulate T1 and T2 for all the time interval in which the vector VU is within this sector. Okay, so it means that, for example, when theta is when theta is 0, so when the vector lies exactly onto the space vector V1, it means that I have just to apply V1 and not V2. So T1 is, let's say, 100% duty cycle. Then increasing theta, I have to decrease a little bit the interval T1 in which I apply V1, and I have to increase the time interval in which I have to apply V2. Okay, up to the point in which theta is 60 degrees, and so we are in that situation, in which T1 is null and T2 is 100% duty cycle. But for that time interval in which VU is inside the sector 1, I have to apply V1 and V2. Okay, so suppose that we are in the sector 1. So this is my hypothesis. But of course, this hypothesis can be extended when the rotating vectors, as they changes the sector. VU is in sector 1. So this means that I have to apply V1, V2, and the null vectors. Let's start with the consideration that I just need one of the two null vectors. Okay, supposing that I want to use V0 and not V7, because mathematically I just need one of the two null vectors to modulate the amplitude and changing, say, the direction of the resulting vector. So supposing that I am in this situation, I applied V1, and so this means that Q1, Q3, and Q5 are 1, 0, and 0. And this vector is applied for a time interval T1. Then I applied V2, and then means that Q1 is 1, Q3 is 1, Q5 is 0, and this vector is applied for the time interval T2. Then I apply the null vectors in order to modulate amplitude. So the three functions are 0, and this is applied for a time interval T0. Okay. Of course, this quantity here, the summation, give us the switching interval. Okay. So the time goes in this direction. Okay, so first I apply T1, then I apply T2, then I apply T0. What does it mean Q1, Q0, Q3, etc.? They are the switching function for our legs. Let me just represent the three legs of the inverters in this ideal form. I have 1, 3, 5 dot switches, 2, 4, 6 that are the even switches. Then I have A, B, and C. So, for example, the V1 vector means that I have this situation here. Okay. Then I pass from T1 to the time interval T2, in which I applied the vector V2. That means that I have to change this position here. Okay, so I'm changing just what happens in the leg B. The leg A and C are not, say, involved. Okay, so I have a switch that just involves the leg B, but not the leg A and C. What happens when I pass from the time interval T2 to the time interval T0, in which I have to apply these null vectors V null? It means that I have 0, 0, 0. So the situation is the following one. Now I change also the what happens in the leg A. So I have two switching action that involves A and B again. So here I'm, this phase here, I'm changing the position of two switches. Okay. Suppose that I want to minimize the dynamic dissipation. You should know that when I switch, change the position of a switch, I change the status of a switch from on to off, I have a commutation, and this commutation leads to, let's say, a dynamic dissipation. When the switch is closed, then we have a static dissipation, but the dynamic dissipation could be, let's say, a little bit higher or much higher than the static dissipation, depending on the frequency, etc. So if I want to increase the efficiency and to reduce a little bit the overall dissipated power, I can think of a different, say, sequence of the space vector to be applied to get the same results, but to minimize the, say, number of switches that I have to switch. Okay, so let me to change this situation into this other one. I have, let me put here Q1, Q3, and Q5. I applied V1, 1, 0, 0, 41 time interval, then V2, that provides 1, 1, 0 for the time interval T2. And then, since I know that it's not mandatory to use, say, V0 our null state vector, I can use, with the same exact result, V7, okay, which is another null vectors. So let me consider what happened with the application of V7. I have V7 here. They both Q1, Q3, and Q5 are 1, and this is applied for a time interval T7. Again, the summation here provides you the switching period. But now look at what happens in terms of, say, commutation. Of course, changing from V1 to V2 brings you the commutation of the leg B, as I said before. Okay, but now from V2 to V7, I have no more two legs switching, but I have just the legs, which is the leg C, which is switching. So in that situation, I have one commutation less than previous situation. Okay, so this combination here, V1, then V2, then V7, in terms of overall power dissipated, has benefit with respect to the previous one, V1, then V2, then V0. So this is to be preferred in terms of dissipation. But now, what I said before, that until the rotating vector is inside the sector number 1, in this example, I have to use again this sequence. Okay, the combination should be always V1, V2, V7. Maybe T1, T2, and T7 are not the same as before, because the rotating vector is, say, can change its position, increasing the angle theta. Okay, so let me just to consider what happens continuing for the second time interval Ts. So V1, then V2, then V7, and Q1, Q3, and Q5. Then I have 1, 0, 0, 1, 1, 0, 1, 1, 1. And this is the first Ts period. Okay, this is T1, this is T2, and this is T7. Then I have to restart. Okay, because I'm supposing that after Ts, the vector, the rotating vector, is, say, still in the sector number 1. So I have to apply again V1, 1, 0, 0. I have to apply again V2, which is 1, 1, 0 in terms of switching function, and then V7, which is 1, 1, 1. Maybe T1, T2 are slightly different, T1 prime, T2 prime, and of course T zeta prime, but the summation of the three should be TS again. Okay, so look at what happens in terms of, say, commutation. These are the two commutations that involving the leg B and C for the first TS period. Then the second TS period, you have, say, let me change the color here. Here, two commutation here, then another one here, and another one here. So here in this sequence V7 to V1, okay, I have again two commutation involving the leg B and C again. But a situation which is much, say, that give us much benefits in terms of power dissipation is to invert, this is the time, okay, the sequence in the second time interval Ts. I can change the sequence from V1, then V2, then V7 into V7, then V2, then V1. Nothing changed in terms of average value, okay? I just change the sequence. V1, then V2, then V7. It means that I have 1, 0, 0, 1, 1, 0, 1, 1, 1 for the first TS interval. The second one will be V7, V2, V1, and say you have 1, 1, 1, 1, 1, 0, 1, 0, 0 for the second TS interval. So I have this commutation here, and then I have this commutation here. As you can see now, I saved, say, at least, say, two commutations. I saved some, say, dynamic power to be dissipated. I increased the efficiency, okay? So nothing changed in terms of average value. I just changed, I reversed the direction. Then it will be, according to this discussion, it can be shown that a much better, let's say, balance among the switching action and the harmonic distortion can be obtained by inserting a null state, another null state, which is V0, at the beginning and at the end of this sequence. So dividing this interval, which is T zeta, in T zeta over 2 here, and for the first one, and adding 0, 0, 0 here. As you can see, adding these null states here increases a little bit the power dissipation because I added two, say, commutation, okay, and so I get the same results that I have here in terms of commutation. But in order to, let's say, have a much better total harmonic distortion, so a low harmonic distortion, so a best symmetries in my unitary switching function, this solution proves to be better. So this is a say, balance in terms of power efficiency and the quality of your sine wave at the output. And this is proven to be the best solution. This is what I applied in my previous discussion. Okay, if you look at what happens here in terms of Q1, Q3, and Q5, okay, you can see that Q1, for example, let me have a plot for this solution. Q1, Q3, Q5 are, say, first I applied V null, so I have 0, 0, and 0, and then I applied V1, and then it means that I have Q1, which is 1, and then I have 0 and 0, so 1, 0, 0. Then V2 must be applied, and so I have 1, 1, again 0, and then I invert the sequence. Okay, no, sorry, I have also V7. So V7 is the 1, 1, 1, and then now I have to invert the sequence. Okay, I have to invert the sequence. So I have V7, which provides 1, 1, 1, V2, which is 1, 1, 0, and V1, which is 1, 0, 0, and then V0, 0, 0, 0. Okay, this is my TS period. So the unity switching function basically get this symmetry around this axis here, okay? And if you get the Fourier series of the output voltage you can obtain by using this sequence, you can have, say, minimization of the amplitude of the harmonics, the higher order harmonics, higher than F1. Okay, so this means that you can have the minimum possible total harmonic distortion, which can be minimized also with respect to the sinusoidal pulse width modulation. So the behavior in terms of output sine wave quality could be better than that of a sine wave pulse width modulation, okay, which is the linear technique that I discussed as first in this contest. In this, say, this discussion try to clarify graphically why I have to use both V0 and V7 as null state in the application of this technique. The procedure I showed you before, the procedure that computes this, say, interval of time T1, T2, and T zeta, it can be totally automatized. Okay, so basically, according to what are the requirements in terms of alpha and in terms of theta, so in terms of, say, switching, in terms of frequency F1, this interval can be computed automatically. So this technique is very easily to be, say, applied to digital control systems in which these equations, okay, that are trigonometric equation for deriving this interval can be stored in form of a, say, digital code program into a memory of a microcontroller, microprocessor, and so this is the way which is typically done in today drives for these three-phase inverters. Okay, basically this can be done in this form, which is, I'd say, a typical digital form. This is an algorithm that you can implement digitally. Okay, but this can be also, say, performed in an analog way. Okay, it can be shown, and I don't want to show here, but I just want to give you as a, say, results that you can implement the space vector modulation by using the typical analog modulator in which you compare a triangular waveform with a control voltage. Okay, and specifically you can get this result, so the space vector modulation, by having, say, a control voltage which has this specific form. Okay, if you are using a standard classical pulse width modulator in which you have a control voltage which is the standard sine wave at frequency F1, like this. Okay, and you add to this control voltage in a similar way that we used for, remember, the third harmonic injection. We have a control voltage, and then we have a third harmonic, okay, which is another sine wave. Then here, it can be shown, it has been demonstrated, then the space vector modulation can be obtained analogically in this way by adding to the sinusoidal control voltage a other control voltage, which is is not exactly here, is okay. A triangular waveform. If you add a triangular waveform to this control voltage here, that has a period which is exactly T1/3, okay, with specific amplitude, etc., then you can get a space vector modulation. Okay, so in that way, the summation of the two provides something which is, say, if you sum the two control voltages, we control triangular, the summation of the two is something like this. Etc. So even here, you can see that there is a strong contribution of this negative part on reducing the peak of the sine wave, exactly in the same way we did for the third harmonic injection. The waveform is not exactly the same because now we have a triangular wave, but basically these, they justified in analog terms, if you want, that by the standard comparison between the control voltage and triangular waveform, why we can enlarge a little bit the linear pulse width, linear say region of operation by about more or less the 15%, which is the same result of the third harmonic injection. But this is not a third harmonic injection, okay? The third harmonic injection is just when you add a third harmonic of the frequency f1. Now we add a control voltage which is a little bit, say, different, is a triangular waveform, and this can be obtained also in this way. While I have to say that 99% of the time this is digitally obtained. Okay, in the slide, I want to share this slide. I gave it to you. I provided at the end of this block of slides a sort of algorithm that can be used digitally for calculating the T1, T2, and T zeta for the rotating vector. Okay, so this is the written, say, by simple words, a possible algorithm for the generation of the rotating vector, so something that can be employed digitally. Okay, have you questions about this discussion? Something which is not clear? Something that maybe requires more explanations? Okay, this part ends the discussion about the space vector modulation and ends the part about the inverters. Okay, I'd like to start now the last part of this course, which is the part in which I'd like to describe the very basic operation of drives, electronic drives for driving brushless DC motor. Okay, so before starting this discussion about the brushless DC motor, I'd like to remember something about the rotating machine. Okay, this is the part, these are the slides that I discuss with the students in electronics, okay, because I know that students in mechatronics basically have much more information, say, about this topic, so they can say know more than I'd like to present to electronics students. So basically, the information that we need in this course are included here in these slides. Okay, and I want to remember just two basic things. One is about the DC motor. Okay, DC motor is a specific type of rotating machine. Okay, so we have a stator, fixed, and a rotating rotor part, which provides the, say, rotating of the shaft of the motor. And it is represented in this, say, cross section here. I just want to point out something that I explained, that in DC motor, in order to produce a continuous torque, I need for a DC power excited for the DC power provided to the stator winding, and an AC power provided to the rotor winding. Okay, so DC motor have, in order to generate a continuous torque, DC supply at the stator, AC supply for the rotor. Practically, how can you say generate this field? Typically, the stator has, let's say, the DC power, which is provided by permanent magnet. So there is no winding in the stator, wounded around the stator. There are DC say power, which is generated by permanent magnet that are embedded into the stator. So no windings, no wires exit from the stator in the DC motor. So in that solution, I have just say windings on the rotor, and I have to supply AC power to the rotor windings. But basically, this is not how a DC is supplied. A DC motor is supplied by a DC power applied to the rotor winding, because between the DC supply and the winding excitation, there is a mechanical fixture, which includes commutators, which includes brushes, that convert the DC energy into an AC form. Okay, the AC form which is needed for the production of continuous torque. Okay, so let me just to share the whiteboard to point out this quantity. Okay, DC motor. So here the topic is brushless DC motor driving. So DC motor have DC stator excitation by permanent magnets, and AC rotor, which is also called armature, excitation by supplying a DC source to a mechanical fixture that includes brushes, commutators, mechanical commutators. So they are mechanical fixtures. Okay, so what is the, let's say, the drawback of this kind of DC motor? Is the maintenance. Okay, because since you have this kind of mechanical fixtures that are needed to convert AC into DC, which is required for continuous torque production, this mechanical commutation causes, first of all, say, acoustic noise, electromagnetic noise, they need periodical maintenance, replacement. Typically, the working hour of this kind of DC motor depends on the size of the motor, but say 1,000 to 3,000 hours of operation continuously can be, say guaranteed. That then we have to replace. Then we have to spend money to maintain or change the brushes, etc., etc. So this is something that is today is something which is considered a drawback. So to overcome this problem, several solutions has been, considered, okay, and being taken into account. One of the solutions is called the brushless DC motor. The brushless DC motor, as the word says, basically is a motor in which you don't need the brush to, say, produce continuous torque. So it means that eliminating the mechanical fixture, the users are allowed to enhance reliability, okay, because of course you need, say, less replacement, maintenance, you spend less money, etc., etc. But not only, you eliminate a heavy and, let's say, large component of the motor. So it means that your motor is light. For the same power ratings, a brushless motor with respect to a DC motor can be lighter. And it means that the inertia that you can get with the same power rating of DC motor in a brushless DC motor can be larger. So larger inertia with the same size of the motor. Less maintenance, so less money to spend for these motors. Let me consider the cross section of this motor, okay? Because it's not only a matter of eliminating the brushes and the commutators. Basically, the structure is a little bit different with respect to that of the DC motor. It's a little bit different because typically what happens is that the construction is reverse with respect to the DC motor. In the DC motor, you have that the stator, permanent magnet, the rotor is DC supplied by the mechanical fixture. So you have permanent magnet on the external side and windings on the internal side. In the brushless DC motor, the situation is reversed. So brushless DC motors have also different construction. We have permanent magnets on the rotor. So it means that the permanent magnets are not on the external surface, on the stator, but are inside. And then you have conductors winding on the stator. Different construction with respect to DC motors. So the situation is reversed. So let me just to show you the cross-section of another motor that has similar construction. So let me share again the synchronous motor. The synchronous motor is a specific kind of AC motor, okay? And I show you at that time that this is the cross-section of an AC synchronous motor. In this cross-section, you have windings on the stator and on the rotor. But remember that one of the possible implementation construction of the synchronous motor is to avoid the winding on the rotor and placing their permanent magnet. While this is possible because in order to produce a continuous torque in AC synchronous motor, you need stators that should supplied by AC power and rotor with DC power. But as we did for the DC motor, in which the DC part is replaced by permanent magnet, even here, typically, the winding on the rotor are not present. They have just permanent magnet. So in the standard construction of synchronous AC motor, you have permanent magnet on the rotor and winding on the stator. But this is exactly the way I just said brushless DC motor are constructed. So basically, brushless DC motors have a cross section that remember that of a AC synchronous motor, specifically what is called the permanent magnet synchronous motor. PMSM, the acronym of this motor is. While the characteristic of this brushless DC motor are basically that of the DC motor. So the brushless motor have same, say, mechanical feature and typically the same power ratings of DC motors, but they have the cross section of a permanent magnet synchronous motor. So it's something which is in between. I cannot say categorize the brushless DC motor into DC motor or into permanent magnet synchronous motor. There's something which is in between. This is the reason why my classification here, I put a brushless DC motor exactly in between. Okay. And this is one of the characteristics that you can have. So let me just to share the slide that you can have for brushless DC motor that exactly summarize what I said up to now. Okay, this is the drawing of a DC motor showing you the large, heavy, and part which is composed by commutators, brushes that is needed to convert AC into DC, sorry, DC into AC supply for the rotor winding. Okay, and then this is the DC motor having permanent magnet on the stator and winding on the rotor, while the brushless DC motor has the opposite construction. Okay, so another benefit rises up when you put winding on the stator, so on the external shell of your motor, instead of having the conductors on the inside as in the DC motor, is that when you have a current flowing into a coil, into your conductors, due to the ohmic losses of the conductors, it generates heat. Okay, and so you have to, let's say, make this heat to be, to go into the air to reduce the temperature of your, say, motors, for example. Okay, you have to make easy the vanishing out of this heat. And if you have conductors that are heating on the inside of your motor, it's much more difficult to say get rid of the heat generated inside the winding. While if you have conductors on the outer shell of the motor in the stator, this can be much more easier. So that means that you can have a power density which is higher. So you can develop higher power ratings without worry about the increase in the temperature, because the air that is around the motor make easy to, say, reduce the increase of the temperature due to the same current. Okay, so this means that brushless DC motor that have this feature not only are motors that have no maintenance, can have less money to be spent for maintenance, etc., replacement, but then can have a higher power density. Okay, you can increase the current flow into the motor without, say, having the same increase in the temperature in the conductors. Okay, they have a low inertia motor because I said before you avoid the presence of all these mechanical fixtures here, so they are lighter with the same power ratings for the DC motor. Okay, so they have many advantages that can be discussed in these terms. So the brushless DC motor that are this acronym here, BLDC, is something that you can find between the permanent magnet synchronous motor. The permanent magnet synchronous motor, sometimes in literature or in catalog, are also described as brushless AC motors, okay, because the construction is very similar. So sometimes you can find BLDC motors, that are the motor I'm just discussing here, and BLAC motors, that basically are synchronous motor with permanent magnet synchronous motor, okay? So this is in terms general, very general discussion, general terms of construction, etc. There are some other characteristics. Another thing that I have to mention here about this, say, overview of mechanical characteristics is that since the motor, the brushless DC motor, has low inertia with the same power ratings with respect to DC motor, they can rotate at higher frequency. Okay, so the rotating speed with the same power ratings of DC motor is much higher because the inertia is less. Okay, so another characteristic is the way you make this motor to be operated. Okay, without entering into much details that are not my field really, but brushless DC motor are designed in order to develop a specific trapezoidal back EMF. Remember what the back EMF is. The back EMF is the voltage that you can have in, I would say, conductors moving inside a space in which you have a magnetic field. Okay, this is the voltage that you can measure across these wires due to the fact that this conductor is moving to a region of space where you have this magnetic field. And the construction of the brushless DC motor is made in order to develop this back EMF that has this trapezoidal waveform. This can show is indicated here. You can see here. So what is the difference between now this motor and the permanent magnet synchronous motor? Maybe the cross section of the two motors, BLDC and BLAC, is similar. Okay, you have permanent magnet on the inside, winding on the stator side, but then the difference is huge if you look at the back EMF, because in the AC motor the back EMF is sinusoidal. Okay, is a sine wave at the fundamental frequency. The back EMF in the brushless DC motor is trapezoidal. The motor is constructed, the position of the wires and the position of the permanent magnet on the rotor are studied in order to develop this kind of back EMF, okay? So what is needed for a permanent magnet synchronous motor to develop a constant torque? In order to develop a constant torque, you need the current, the current flow into the winding, okay, the stator winding of the permanent magnet synchronous motor, which is an AC current, should be an AC current with the same phase of the back EMF. Okay, and this is useful for generating the constant torque. In the brushless DC motor, since the back EMF is, say, trapezoidal, you need a constant current flowing through the motors, through the windings, the stator winding of the brushless motor, in order to generate a constant torque. Okay, this is the basic operating difference between the two. Okay, for example, this characteristic for the permanent magnet was exploited in the AC three-phase voltage system or one-phase inverters. Okay, in which I have to generate a sinusoidal fundamental frequency at the output in order to drive, say, the AC motors for generating a constant torque. Okay, if I know that my motors must be supplied with a, say, a current having frequency F1, I apply my switching action on the one-phase inverters or three-phase inverter in order to generate this harmonic component. Okay, all my discussion about inverters was to develop a phase current, which is, let's say, sinusoidal frequency, sinusoidal waveform with frequency equal to that of the back EMF. I need the fundamental frequency component in order to generate constant torque. But here the situation is different because, say, now we have a trapezoidal back EMF, and so in order to get constant torque, we need a constant current. So why we need a constant current for a constant torque? Let me just do show you briefly here. Okay, remember that we have a mechanical power. Okay, the mechanical power, let me call it this PM or PM, yes, PM. The mechanical power is the product of the torque developed by the motor multiplied by the rotating speed of the motor. Okay. Then you have an electric power, which is given by the product of the back EMF, basically, and the current. Suppose that A here is the phase that I want to consider now in this example. So what happens is that the mechanical power, the electrical power that I provide at the exit of the output of my inverter, of my drive, is converted into mechanical power. Okay, so I have that EA multiplied IA is the product of the torque multiplied the speed. So the torque, which is developed by the motor, is the product of the back EMF, the current divided by the rotating speed. The back EMF of brushless DC motor is something like this. So here is constant. This is a trapezoidal waveform. When this back EMF is constant, this quantity is constant. Okay, if I provide a current which is constant during this interval in which the back EMF is constant, it means that you have a product between two constants. Remember that the back EMF is something which is proportional to omega m. Okay, increasing the rotational speed, this back EMF is increased. So it means that if here the back EMF is constant, this quantity is constant. So in order to get a constant torque, you need this constant current. Okay, only a constant current here can provide you this feature. The same reasoning can be performed for the permanent magnet synchronous motor, showing you that when you have a back EMF which is sinusoidal, you need a sinusoidal current to get a constant torque. Okay, basically, so just roughly speaking. Okay, so I will stop here, and then I will continue next Tuesday at 10 a.m. because I don't want to stop. I want to start this topic from the beginning without the breaking. Okay, I have to say that Wednesday 26 I will finish lectures. Okay, so I have just to finish the brushless motor that I just started now, and Tuesday and Wednesday. So also Wednesday, I will provide you some basic information about the examination, okay? And then I will say, it will be available for say from now to the next examination, etc., for some consulants, for some questions regarding the topic of this course. I uploaded files into the Materiale section of the students portal for simulating in SPICE, LT SPICE, three-phase inverters, okay? Both in linear and square wave modulation. So if you want to, say, play a little bit with simulation, you can use that files, okay? If you have a question about what I'm saying now, I can answer a question. I have a question here from Marco Cannone. There is a book or an application note dedicated to digital control for the inverter. Okay, there are several books, but there are very few books that are good. Okay, so I can suggest you. Can you please send me an email? Okay. And then I reply to this email by suggest some say, titles, okay, providing you this information. Digital control for the inverter there are some books for digital control for the inverter. There are books for digital control of power electronics that are, say, a much wider topic. Okay, they can suggest both of them. Okay, other questions? Okay, guys, thank you very much. Have a nice day, evening, and weekend. We can see each other next Tuesday, 25. Bye.